Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if we can actually build mathematical models of depression from real-world data? Well, this new study might have a clue. Imagine trying to understand something as complicated as depression, not just by talking to people, but by building a mathematical machine that mimics how it works. That is exactly what these researchers, Sophie, Engels, and Joshua Curtis, set out to do. They're not just thinking about depression as a list of symptoms, but as a dynamic system where different parts are constantly influencing each other, changing over time, and sometimes even reaching tipping points. Traditionally, scientists have created these mathematical models for things like panic disorder or suicidal thoughts based on what they think is happening, and then they test those ideas with simulations. But the problem is, those models might not perfectly match what is actually happening in real people's lives, they might not have the right timing or the right amount of detail. So these researchers decided to flip things around. Instead of building a model first and then trying to fit data, they wanted to use data to discover the model itself. Think of it like this. Instead of having a recipe and then trying to cook something, they looked at a bunch of delicious meals and then tried to figure out the recipe from the ingredients and how they were put together. They used a powerful method called sparse identification of nonlinear dynamics, or SINDy for short. This method is super cool because it takes a bunch of potential mathematical building blocks, like simple lines, curves, or even wiggles, and then uses a clever kind of math called sparse regression to figure out which of those blocks are actually important and how they fit together to describe what is happening. To do this, they focused on a well-known idea about depression called the behavioral activation model. This model suggests that when people stop doing rewarding activities and start avoiding things, their mood gets worse, which then makes them even less likely to do things, creating a downward spiral. They decided to see if they could find the mathematical rules for this cycle using real data. And what kind of data did they use? This is where it gets really interesting. They used data from a study that collected information from people's smartphones and wearables, along with their self-reported feelings. Specifically, they looked at things like how far people moved around each day, mobility radius, how much they communicated with others through calls and texts, aggregate communication, and how many different people they talked to, interaction diversity. They also use symptom assessments like the PHQ-9 and PHQ-2, which measure depression and anhedonia, the inability to feel pleasure. They basically turned daily behavior and feelings into numbers that a computer could understand and analyze. So how did they use SINDy with all this information? First, they used a statistical technique called generalized additive models, or GAMs, to look at the general trends in the data for the whole group of people. This helped them see if the relationships between things like communication and mood were simple straight lines or more complex curves. They found that the relationships for anhedonia and depressed mood were definitely not simple lines. They were quite wiggly, suggesting a lot of nonlinearity. Using the trends they found with GAMs, SINDy then went to work. It looked at a whole bunch of possible mathematical functions and figured out the simplest set of equations that could describe how these variables changed over time for the average person. This gave them a nomothetic model, which is basically a general model for the whole population, the R. Squared value of 0.69 means this general model explained about 69% of the variation in the data, which is pretty good. But here is the catch with general models. People are different, right? What is true for the average person might not be exactly true for you or me. So, they also tried to create idiographic models, which are personalized models for each individual. They used a method called Markov Chain Monte Carlo, or MCMC, to try and find the best fitting numbers for the equations for each person separately. When they compared the general hard model, the nomothetic one, with the personalized soft model, they found something interesting. The personalized models didn't always do better. Sometimes the general model was actually more accurate, but other times the personalized model was better. This suggests that a one-size-fits-all approach isn't perfect, but neither is a completely personalized one for everyone. They also noticed something really important when they looked at the differences between the general model and the individual models. For example, in the general model, mobility seemed to have a positive effect on depressed mood, which sounds a bit weird. But when they looked at individuals, mobility actually seemed to reduce depressed mood. This kind of mismatch, where the overall trend is the opposite of what you see within individuals, is called Simpson's paradox, and it highlights how crucial it is to consider individual differences. The discovered equations also gave them some really neat insights that they might not have guessed from just reading about the behavioral activation model. For instance, they found that interaction diversity, how many different people you talk to, was the only variable directly influenced by depressed mood. This gives them a concrete mathematical link between mood and social behavior. They also found that depressed mood seemed to have a dampening effect on itself in the equations, which could be a way for the system to prevent things from spiraling out of control too quickly, a concept seen in other complex systems models. One of the big takeaways is that using data to discover these equations is super powerful. It can reveal complex, nonlinear relationships that are hard to figure out just by thinking about them theoretically. They also found that while the general model was useful, there were many parameters that varied wildly between individuals, meaning a purely general model might not capture everyone's experience accurately. This leads them to suggest that a combined ideo-nomo approach, where you blend general principles with individual adjustments, might be the best way forward. Now, of course, every study has its limits. This research focused on the average trends and didn't try to discover completely different equations for every single person. It also depended on the specific data that was available. But the exciting part is that this method could be used for all sorts of mental health conditions. Imagine applying this to anxiety or even addiction to build data-driven mathematical models that truly reflect how these conditions unfold in real people. In conclusion, this study shows that we can move beyond just theorizing about mental health and start building sophisticated mathematical models directly from data. By using clever techniques like SINDy, we can uncover the hidden dynamics of conditions like depression, get a clearer picture of how symptoms interact, and pave the way for more personalized and effective treatments. The idea of building mathematical machines that model our minds is no longer science fiction. It is becoming a powerful tool in understanding ourselves. What do you guys think about using math to understand our minds? Does it feel too cold, or does it offer a new kind of clarity? Let me know in the comments below if you found this as fascinating as I did. Give this video a thumbs up, and don't forget to subscribe to Rubin's Mind Lab for more deep dives into the science of the mind. Thanks for watching, and I'll see you in the next one.